Okay, so we are going to start the layout of the pump, and then we have our cell here. We open the schematic, and when we open the schematic editor, normally the standard Virtuoso schematic that is open is the version L. Okay, so what we have to do is to launch the schematic XL, which is the one that has the tools that we are going to use for layout, modern layout of the differential pair and the current mirrors and other parts actually we're going to start working with. So we check that the Excel has been open. It is here, and then we go to window assistant, and then we open the constraint manager. Okay, so we have the constraint manager already open here, and then we start, and we're going to start with the differential pair. Okay, so we select both transistors in the differential pair. Here they are selected, and then we go and we just left click the module generator, and then what we have is that new window will open, and it is a layout window. Here. Okay, we press F, and then we see all the components from the differential pair. All the transistors are already here. Now the first thing that we have to do is to decide the placement of these components. We know that we have to interdigitize this one very nicely, and the question here is how many rows are we going to use and how many dummies we have to add. So we're going to start trying a few configurations so that we can find the number of rows that we will need. So typically for a differential pair you might need 2 rows. Okay, so we see here we have an aspect ratio that it is quite nice, around 3:4. So we will most probably do the layout with 2 rows when we place the dummies in this one. So for two rows, we will need dummies on the right or on the left side. So we need to add those dummies. So I will just go back to my schematic. Here I'm going to delete this modgen, and then I will add the dummies. For that I copy just one of the transistors, and for the dummy I short circuit the drain, gate and source, because these transistors will do absolutely nothing. They are just going to be improving the matching. The bulk of this transistor was connected to analog ground. And then we have here the option where to connect the drain, gate and source. We can connect to any net, and the candidates will be the analog ground or the node B. That will be probably the best candidates. If we connect the dummy transistor to node B, it will be a little bit easier the layout, but it will add some capacitance from B to ground. If we connect it to the ground, we will see that it might add a little bit of layout. We will need to do a little bit of more layout work, but it will not add this capacitance. So we are going to go forward and then go to connect this node to ground A. Okay, so we have basically all the things that we need to change this to multiplier of 4, because we just need 2 dummies at the left and 2 dummies at the right. So we have 4 dummy transistors, and then again we select this transistor, we select the dummies, and we left click the mod gen, and then we have all the transistors that we are going to connect. Now we go back to the pattern generator. We are just going to use the custom. We put 2, that it is a reasonable number of rows that give us a compact rectangle, and then here I will work on this pattern because I need to interdigitize with a common centroid. I delete these ones, and then I'm going to put all the transistors. So remember, the left transistor of the differential pair that has been selected first takes the letter A. The second transistor that has been selected, that was the right transistor in the differential pair, is B, and the dummy is C. So we have 10 components for each AB and 4 components for C. So let's place the dummies first. So we place the dummies here, and then 10 transistors for transistor A. It will be 5 transistors on the top and 5 transistors on the bottom, and then the same for B, and then we start the interdigitation of these transistors. It will be B here, 2, 3, 4, and 5, and then we do the same at the bottom, but then we change the pattern. Okay, so now take a look to this detail. We have 5 transistors on the top and 5 transistors on the bottom. This is an odd number. So if it is an odd number, it means that at the middle we will have, I mean, for the common centroid precisely in the middle, we will have half of the transistor B, and A will be exactly divided by the centroid here. So if we have an even number of transistors in each row, that will be a complete transistor on the left, on the right, and we can do the interdigitation exactly as it is in the we did it in the lecture. Okay, so but this pattern is quite okay. You can see there is a perfect zigzag here. A's and B's are doing a zigzag, and the same number of transistors are on the top and in the bottom. So it is quite a good interdigitized device. We apply, and then it has been reordered the structure. Now what we are going to do, it is we're going to change the spacings. We want them as close as possible, because the mismatches are also a function of the distances. The closer the transistors are, the lower the dispersion of the process variations. So we're going to place them at the minimum distances. So we have selected all the transistors, and now I'm going to select member alignment spacing. Then I'm going to select custom, and then I'm going to select a layer for this is the diffusions. So this is the minimum space for diffusion between transistors is 0.28 micrometer. So this is the minimum before the DRC start throwing errors. So I'm going to use this one, apply, and then you see all transistors have been compacted. So let's check, let's take a look. So the red color is the diffusion. So we're going to go to the measurement with K. with key. So there is 0.28 micrometer. Shift key will delete the measurement tool. Okay, now the transistors are nicely placed. Now I want you to notice something that maybe I forgot to mention before. We have metal contacts to the gates. Okay, I will just close for a second the module and show you where does this come from. So we click the transistors here. There are options for the layout, and I have decided to add gate contacts on the top for all transistors that I'm going to lay out. And then there are many options to play with here. But I decided to do this in this particular case. So each transistor will have a metal contact on the top. Okay, so we go back, double click the module, and then we go back, continue working with the module, and we see that the module has already been placed nicely. Now what we're going to do now, we're going to flip the top transistors, and then we flip vertically, so we have the gates facing each other. So because what we're going to do next, it is we're going to pass both the input connections here in the middle. Okay, we have placed these ones, and then we're going to use very much the single track and the trunk topologies to do the layout. So these are the tools that we're going to use during this tutorial. So first we're going to create a single track topology. So we click here, and we have the following menu. Here we can select the net that we want to lay out, and we are going to start with the input. The layer that we are going to route, it is metal 2, so I'm going to draw a metal 2 connections that go all over the center here, connecting the net the positive input. The width, by default, it is selects minimum width, but we should not use minimum width or minimum spacing for what matters, with the exception of that we place the transistors that close together. We should then use the minimum devices or minimum width for the connections. So I will be using here 0.4, or we can use even 0.5 for the connection. And for the spacing also, I'm not going to use 0.28. I'm going to use something a little bit larger. So the minimum spacing for more than 0.5 micrometer width, it is 0.34 in this technology. So we're going to put that one. And the last thing to do is that I'm going to configure the width of the twig that it is going to connect. The twigs are the connections, the vertical connections that are going to be created, and those should also be 0.4. Okay, so with that, I am ready with the configuration. So what I can do here, it is just to pass one left click, and then we just passed a line, second click, and it will create this connection here. So I press ESC, and we see that a metal 2 track has already been created, and the tool has detected what are the nodes that need to be connected. So each of these one is called a twig. And if I want to see how the routing will be done, I can just click this generate routing from topology, and we see that automatically the layout has been generated. Okay, so it has created these connections. These connections are 0.4. The trunk it is 0.4. This is the twig 0.4. It has been automatically layout. I can remove the layout by clicking this, but that will, that will still keep the trunk here. If I want to remove the trunk, I can delete it, all the trunks by selecting delete all topologies and routing. It will basically remove everything that I have done. And yep. Still, I can use the keys U for undo if I want to come back. So I will keep it like that. If I don't want to see the twig connections here, I can remove this one, and then sometimes it improves the visibility, but I will going to leave it as it is right now. So I have laid out the positive. Now I am going to lay out the negative. So I go to create single trunk topology again, and when I open it again, it saved some of the configurations that I left in the previous run, but not all, unfortunately. So I will have to repeat the spacing, for instance, every time. So I will have to change this to 0.34, 0.34. The rest of the configuration is the same. Now I change this one to the negative, and then I can place it somewhere here, and then it creates another connection here based on the configuration that I sent. I press ESC, and then let's take a look how it looks, this routing. And yeah, we can see that the routing has been done. Both for the positive and negative, and it has been done respecting the spacings. So it has 28, which is enough for passing DRCs, and the connection asymmetric, so there is equal parasitics for the positive and the negative, so it has been much parasitics here. Yeah, and I hope you already start appreciating how easy this layout can be when it is done using this tool, because this might take some time if it is done manually. So let's remove this one. So let's look how it looks like. We see the contact, metal contact there. Okay, so we go forward, and now we are going to lay out the source and drains, and then we start with the sources, and for that we're going to continue using the single trunk topology. Yeah. The source of this circuit, it is the node, and then we need the help of the schematic. The source is the node B. Okay, so in a differential pair, it is much more important to lay out first the sources than the drains, because every impedance that we add to the source of the transistor will create a voltage drop, and basically will add some some feedback, some negative feedback at the source of that transistor. So we have to be a little bit more careful with this layout of the source than to the drain. And an impedance that is added to the drain, it is not normally so problematic. So we are going to lay out the source first because it gets closer to the transistors, and we select the source, that is B, and now we need to use the information that we have for the current, okay, the current densities. The current densities, we check in the manual the current densities for the metal layers in order to decide the width of the connections. In this particular case, these are ultra low power designs. We are talking about microamps. It might not be so serious, the situation, but there are cases in which we are designing amplifiers that consume milliamps. Then we have to be extremely careful with the width of those connections. In this particular case, it is the 1 microamp passing through each transistor, so the totality is 2 microamps for the node B. The current density, the maximum current density for this technology, for this metallization layer, it is typically around 1 milliamp per micrometer, but you have to check in the manual. So we can in principle use minimum widths, but they are not recommendable. So for this exercise, I'm going to use 1.5 micrometer, which will allow me to put a few contacts, because there is another issue also when we are doing analog layout. It is that we should try to avoid very few contacts for reliability issues. We change the minimum spacings 34, not to play with minimum spacings here, and then I think we are settled with that. So we are going to try here node B, and we can switch on this one to see how it is being connected, and we see that the twig has connected here, node B, and then we're going to do the same down, and we see that it has connected these nodes also. All the transistors have been connected to node B. Okay, so now we are going to connect the drains, and we can start with node C. Okay, so we go back, we press ESC, and then we add it again. Node C, again we need to change this 34, this is okay, and we are going to put one node C on the top. Okay, and then we see that it has connected these ones, and now I am not going to put a node C here. Instead, I will put a node D, because I want symmetric parasitics at both sides. So I'm going to change this one to node D. This goes to 34. Okay. And now I can put it a D on the top and a C down. So I come back to C, this is 34, this is 34, and then I put a C down. So what did I did here? Okay, I added the D and C nodes connected but I want both sides to have the same parasitics, so I put one close to B and one close to D here, one D close to B, so that they have both the same parasitics. So here we can have a preview how that it is going to look. So we click it here. Let's remove for a second the twigs, and then let's zoom in. And here we can see that they have already been connected. They have already been connected, and basically without any effort. Okay, so we continue. Now we are going to do vertical connections for the B, D, and C. We still use the single trunk topology here, and we start with B. That, as I mentioned before, this is the critical node that I need very low impedance, disconnected to the sources. I don't want an impedance there and the source of the transistors. And yeah, these ones are going to be collecting the currents. I will change to metal 3. I can keep it 1.5, 34, 34. And then the twigs will be instead in metal 2 this time. This will be metal 2. And we can have a preliminary routing here to see how it will look. Okay, so it has it has generated a metal 3 connection, and but you can see it has covered the whole way. So I might want to do it like this or might not. It really depends. To keep it the connection from the top to the bottom. I have also the following option if I want. So I can go back here and use the trim trunk, and I can trim it to both sides so that it doesn't overlap the C and D connections. Something that sometimes is useful, it is to allow multiple connections to a terminal, but we're going to discuss this a little bit later. Okay, so we are going to run it here. And then we can see that now we are not overlapping D and C. Okay, so it's reducing some capacitive coupling that might not be very much, but anyway, now it is a little bit better. Okay, we do the same the other side. Unfortunately, I have to bring it again the menu and do this change manual here. It doesn't save my configuration, so okay, so I have done B, and now I'm going to do C and D, and yeah, I hope you are already getting the idea how this works. So now I have the option of connecting both the drains at both sides, or just one drain at one side and one drain at the other side. In this exercise, I'm going to be connecting both. Sometimes it is not really necessary. It's okay to bring only in one. But let's start with C. Again, this is 34. For the two, it doesn't matter in this case. So we are going to connect one C here, and then I will be doing the same for D. And as you can imagine, I will put the D in this side. We can do the D here and also one D here. So in principle, this should be already over here. It is already connected D and C, but if you want, you can connect in both sides to improve to reduce the resistance if you need, at the expense of a little bit more parasitic. So I'm going to do that because we are not constrained by space right now. So let's do that. So there will be 34, and then we're going to add a C, and then that will be here. We add C, and then the last one we're going to add the D here. It will be 34. We add it here, and then basically we have all connections done with the exception of the dummies. Okay, very good. So we have connected the gates, drain, and sources of the differential pair. Now we have the dummies connected to ground, and for that we can either do it here or do it a little bit later. Normally I prefer to do it a little bit later when I'm doing the layout, because there are ways to connect it here, but they are not necessarily the best. Now here, what I used to do also is to generate a word ring. So these are NMOS transistors, the bulk connected to ground. We want to connect a word ring to the ground A. Okay, and we are going to use a P word ring. Spacing, we can try around 0.5, and let's take a look how it looks. And yeah, it didn't go very well. It is short circuiting here. So it is calculating the 0.5 spacing from the transistors. We press U. We try it again. Round A, and let's try with 5 micrometer. A little bit better. They still are being very close to the metals, so maybe I need a little bit larger. Let's see. Let's put it in 6. Okay. So now I have my ground ring here, and yeah, I will defer the connection of the source and drain and gate of the dummies to the layout in when I'm connecting all the modules together, because it's a little bit more easy and it is very much quicker to do it there than try to use trunks for the connections here. That will add more parasitics. Okay, so we are basically done with the layout of the differential pair, so we can click it here, and then it is ready. We can save, and if we need to edit it, we can always come back here, and the layout of this differential pair, it is ready. Okay, so